So today we're going to start with the same code from last time, but I'm going to remove quite many of the functions from there because we're going to start something new. We're going to talk about something new, but I will keep the functions that are still going to be useful for today. So I copied the project under this physics.html demo, and so far it's the same. I'm going to rename the title here. And today we're going to need just one canvas. We don't display multiple things there. I changed its ID back to canvas since there is no need for A, B, and C. And here I'm initializing the canvas. I won't need houses anymore. Maybe I'm going to animate something on it. And maybe I still want this mouse down on it, but let's see that for later. So I'm commenting out this code. The particle class we will keep. I'm not going to use sun anymore or this variable animate particles. Animate particles, I think we will reuse somehow. Let's call it today, we are doing physical simulation, so let's call it simulate. Simulate physics. And I rename it also here, and let's actually call it in the main function. Simulate physics, I'm going to remove this random initialization, and in the set interval that repeats many times per second, right? I'm just going to draw the different particles, so I don't remember what the attraction or whatever we did last time. And I'm not going to draw the sun anymore, so... Okay, vector operations. I will keep everything. Scale vector, get magnitude, normalize vector, add, subtract. Get cursor position may still be useful. These polygons examples I don't need. Clear canvas function, I want to be able to delete it because every time you redraw on the canvas you want to delete what has been there before. Initializing the canvas, it's in use. Houses I don't need. Houses as image, random color, draw house some other way. I don't want these things, so many things go away. Draw the regular polygon is still there. Okay, I will need this to be used by the particle class here when we are displaying a particle. And yeah, let's define a few particles here just manually and put them on the canvas to see if they appear there and if the code I modified now is still working. Okay. So I'm going to say particles. So this is my particles array from here. I'm going to add a new particle to it. So push. Oh, wait, just a second. My keyboard is not the right keyboard. And the language is not the right language. New particle. Okay, if you remember, our constructor for particle needs a location vector and a velocity vector. So I'm going to give it a location of, let's say, 50, 50, and a velocity of 0.8 and 0. Now, as I'm writing these, let's put 4 particles. I'm going to ask you a question and you should answer me. Which direction are all these particles going to go? So these are the 4 particles and the velocity vectors for each particle.
Mm-hmm.
So which direction are they going to go?
To the right?
Right,
To
yes.
the right.
Are they going to go at the same pace?
No.
No. Okay, because the x component of the velocity vector, the first component of the velocity vector is different. I'm going to save the file and hopefully, if no errors, refresh the page and nothing happens. So they don't go anywhere because they are not animating in any way. They are defined with this velocity vector, but they are just being drawn and the location at the location, which is not modified anywhere with the velocity that we specify. So to do that, but we can see them, so that code works. We can see them, the locations are correct, but the velocities need to update all the time. So this is going to be the code where we update locations of particles. So this updates the locations based on individual velocity vectors, right? If you don't, if you have not looked at the physics video I mentioned about vector manipulation, I made some new slides today that should explain to you how they work. So vector addition, you just add the 2 components for each individual vectors and you get a new vector. Subtraction, very easy, you just subtract each component and you get a new vector, this one. Note that all the time, every time you get the new vector, you get it as it would be represented from the origin. Scaling a vector, here I'm scaling it by half and my blue line stops in the middle of the original vector. If you scale it with a negative number, it actually will go the opposite way. So it's quite convenient, and you only have to multiply each component with the scalar, not a vector, a scalar, a number. 0.5, 2, 10, -1, whatever. Okay? Magnitude. The magnitude of the vector is the length of that arrow we're drawing all the time. And you can calculate it with this function. This is just a Pythagorean theorem in 2D space, where we don't need to specify the other point, because the other point is 0. So I would just subtract 0 from all the things. And this way you can write it simpler. Vector normalization. This sounds extremely scientific and scary. It's just scaling by the inverse of the magnitude. So the magnitude is the distance. If you scale by the inverse of this magnitude, you will get a new vector which has a length of 1. So this unit vector is very nice to have, because once you have a unit vector, you can scale it to any value you want just by the scale function. So this was just a quick reintroduction to vectors here. And now we go back to the code and figure out, so okay, our particles here need to move according to the velocity vector. So the location vector of our particles needs to be added. Add vectors. It's the addition between the location vector and the velocity vector that we defined up here. If we do that, then the particles will update their location with the specified velocity at every tick of this interval. Okay? I'm saving the file, refreshing the page, and your guess was right. They are moving to the right. one of them is actually overtaking another one, so quite interesting effect there. And your answer to the other question that they are going at different paces is also correct. So good job. Okay. Now last time we also experimented with gravity, right? So gravity is a vector. It goes 0 horizontally. If we are thinking about this classroom, gravity doesn't push me that way or that way. It just pushes me down. So let's put it down to say, let's put it to 1. Yeah, in this size scene, maybe 1 is going to be enough. But all these particles, so they are now moving with respect to their individual velocity, but their velocity is affected by gravity. So this is something that we need to add to our computation. And the way we do that, okay, so last time in our demonstration I went extremely fast, and some of you definitely got it. I know you did. But I'm going a bit slowly just to make sure that more of you get it. So we update our velocity with the current velocity adding g. And then our location updates with the velocity that we calculated already. So changes in speed caused by the g, which is gravity, or the gravitational acceleration. So acceleration means speed will change. I'm saving the file. Okay, very fast. Something happens, but you may actually not see anything. I will modify this tick interval so that our animation goes slower. I save the file. You may see something, but okay, I'm gonna make it even slower because I'm sharing the screen, so it's not coming to you in a good time. Do you see the particles going down?
And a bit to the right.
And a bit to the right, yes. This point starts a little bit closer to that point, but ends a little closer to the other point. Okay, I'm gonna have to exaggerate these values a little bit. Let's put here 3.8, 3.3, 2.3, and okay, 1.2 and 1.3, and let's look at it again. Okay, so now it should be visible that something is moving. Okay, let's go a little bit slower here. Can Kuopio also tell me if they see movement in these particles? And if they see them moving slightly to the right, but also being accelerated by gravity? Okay, especially these top ones. These top points are moving more because they have the 3.8 and 3.6. So this is the Y component, the smallest. They are at the top. Okay, so particles moving, and they are affected by gravity. Now, I'm going to teach you something a little bit different. It's more or less an idea to learn a bit more about vectors, but it will be a good foundation for making a physics engine today. So I want to explain how you can build a rigid body simulation physics engine using this idea from here. But first I want to remove the velocity. So try to stick with me. Okay. I'm going to remove the velocity component from the particle itself, and I'm going to replace it with a variable called old location. So the idea here is that if I know the current location of a particle and I know the old location of a particle, I can immediately calculate the velocity vector by vector subtraction. So this is very easy, it's one operation. And I could add that to the current location and predict the new location. So this should be quite clear. And of course, as before, if the gravity would have affected in one part of this moment, our new velocity vector can be obtained again from vector addition, and our new location actually moves affected by gravity as well. So I'm removing the velocity, but I'm still going to calculate it for reasons that will remain a mystery for now, but I will explain in a little bit later. The main reason is I want to make sure you understand the vector operations, so we will use vector subtraction here. But the second one and more important one comes later. So I will allow the particle constructor to still have velocity, but I'm not going to store it here anymore. I commented this out. Instead, old location is going to be subtract vectors from the location from the location I subtract the what?
Old location. Current location.
No, so location is the current location, but I actually, okay, velocity is given here. So this velocity is actually given here. I want to go backwards from it, so I'm going to subtract the velocity to get the old location that was never given to us. So the old location, I inferred it even though I didn't change the constructor. And now this simulation here, instead of, we don't have this particle's velocity anymore, right? But we can have a variable of velocity that is found by subtracting vectors. And the vectors that I'm going to subtract are the location and the old location. So anytime I'm going to want this velocity, I can do it by subtracting the location and the old location. And then here I again have, instead of this attribute of the particle's object, I just use the velocity variable from before. So this code, if I didn't make any mistakes, should be identical. It's no change at all as before, but we will see soon what we can do with it. Okay, it's not happening well. Something is not going correctly here. Everything is going to the right. The problem is I still need to update this old location. So this old location stays as the initially defined location, but it should constantly update itself every time we move. So the way I'm going to do that is say new location is equal to this thing from here. So adding the vectors and then updating the components. Old location is going to be equal to the location variable, and the new location is going to go to the location. So in this way I'm constantly keeping track of where the particle was just seconds before, like the previous stick. Let's see now how this looks like. Still some problem there. Oh yes, gravity. I haven't added the gravity, but this was needed anyway. This whole part of code. So the gravity to this new location, I can write as a separate line here so it's not confusing. The new location is going to add also the gravity. So now I can write it like this. I'm going to save the file, refresh the page, and finally, all this work for nothing. It looks exactly the same as before, but the velocity is now calculated on the fly. And it's going to be calculated no matter what kind of forces I decide to add to the elements. This is important. So, because any time this object will move, the new location will update. If, for example, I decide to interact with the object by mouse and move it farther away than the gravity or whatever forces are doing to it, the new location is going to involve my movement, and the velocity updates instantaneously, no matter what kind of things happen to it. And here you should think about friction, collision, all sorts of this user interaction. And you will get a feel of what I mean by this, but yeah, so all you should know now is that I decided purposely to remove the velocity because I want to allow more things to be done to the particles, and that it would still be calculated based on the new movements after the interaction. Okay. Now, okay, some formulas here, you can look at them, but more or less they explain what I did just now. Okay, maybe we just look a little bit. So new location is current location plus the velocity in a time span. We talked about it. The current velocity, we can get it as the subtraction, vector subtraction of the current location and the old location. And the new velocity, we can get it from the current velocity plus the acceleration. And our delta t's, we can consider them, okay, so here I just substituted all these things in one giant equation here. But these delta t's can be considered one time unit. So this one time unit more or less can be ignored, or you can try to play with it and do some slow motion simulations or whatever. You can play with that. But this is the function that we implemented into code now. So subtracting the current from the old, adding the acceleration, and then modifying the existing location with all of that. So should be easy. Don't be scared. Okay, now the fun part begins. I want to present you a method that uses these just this old location and new location to generate a rigid body simulation engine. And the method is based on this paper. It's an old paper written by this Thomas Jakobsen. I hope this loads something. If not, then I have to... Yeah, so you have linked to this paper also on my page. It's a really nice paper, and some of you may relate to it. When the game Hitman appeared, 2001, this idea, all this thing here, and this is our formula from today, okay, with the current location, old location, a little different syntax, but this is our formula from today. So this was used to build humanoid figures that look something like this, okay? And when it's a shooting game, and when you would shoot this humanoid figure in different parts of the body, it will fall in a realistical way. So before that, there were pre-made animations. You would shoot somebody, it will always react in the same way. But now, if you shoot here, for example, he will fall on his left side as we look there. So we will do this today at some point, but bear with me until we get there. So the idea is we need a simulation for objects, not just particles. So these kind of constraints between objects are what we are going to do now. And these constraints are going to appear as segments, rigid segments, or sticks or poles, you can define them, that keep the points always at the same distance as initially defined to each other. No matter if this point is kicked, tossed away, or now we have the initial velocities, right? So what we are going to add is a system for keeping these distances fixed between the individual points. So we are going to need an object called segments. Again, I'm going to keep it as an array there. And I'm going to define it like this. Segments, push, new segment. I will need a new class for the segment object. I will write it soon, but before that, I will just say link particles of 0, so the first particle with the second particle. Okay. Now the second particle with the third particle. I really hate this starting at 0 and saying first, but that we talk about that some other time. The third particle with the fourth particle, and the fourth particle with the first particle. So we get the same thing as in my PowerPoint drawing from before. Now, what will this segment class look like? I'm going to copy this particle class and say here segment class, and my constructor is just going to say particle A and particle B. So 2 particles, and I'm going to store them as local variables or class attributes or whatever you want to call them. And to draw the segments, I'm not going to draw a regular polygon, right? I'm going to draw a line, another function that I actually don't have yet, and it's going to draw it on the canvas from particle A's location, not old location. It also contains the old location here. And to particle B's location. So just a line depicting where the segment is appearing, is existing in our code. Okay, now instead of okay, maybe we make this draw line function, we don't have it. So we have the draw regular polygon function. I'm going to copy that as inspiration, and draw line, it doesn't need all these weird things here, so just from and to, okay? From is highlighted by the Notepad++ IDE here. I think it will work. I think Georgia was thinking that maybe it's going to break because from is used in other parts of the syntax. But let's see what happens. If it doesn't work, we will change it to maybe underscore from or something like that, even though I don't like to do that. Okay, so begin path, move to from of 0, okay, and from of 1, and yeah, line 2, 2 of 0 and 2 of 1. I think this is our draw line function. It should be correct. And in the place where we defined our segments here, our iteration function, this set interval, needs to display, to draw also the segments, right? So I'm going to copy this code, segments length, and each segment I'm going to tell it to be drawn on the canvas. I save the file, I go back to my code, I refresh the page, and particle A is not defined. Okay, I click here this link. Yes, so the problem is in our segments class, at this step right here, particle A, so this relates a little bit with Jarmo's observation from before. So particle A object exists only here. It's a parameter for this constructor. But this particle A exists everywhere. This corresponds to the global scope here. So this is what it was warning me about there, that I need to add this. I save the file, refresh the page, and now, of course, it's not rigid. I didn't impose the constraints in any way, but the object is deforming, so this length especially is becoming, this side here is becoming quite long. And I see the segments that are internally in memory. So it's a good idea not to implement all the code and then run it once at the end, because it will be filled of errors or filled of things that you don't fully understand. Right. Okay. Now, how do I do this? Because it's not that easy, but it also is not very hard. Okay? The idea is, when we have these segments defined, we look at each segment in particular, and we must store its length, its original length when the segment was created. So that's the length that must not change throughout our simulation. So it will be part of our segment constructor. This length is equal to, let's say, distance. I don't have a distance function just yet, but I will make it, between particle A and particle B. And note here, I can either use particle A or this particle A in this, because both of them are existing in this block of code. So I will not get the same warning as before, because I'm omitting this. Our distance function between two vectors needs to be written. So function distance v1, v2. And here I'm going to say two things. You can either treat the vectors as points, because that's how we are defining them. We consider the tip of the vector and consider that the origin is in the 0, 0 coordinate. So the distance between two vector tips is going to be the well-known Euclidean distance between 2 points. v1 of 0 minus v2 of 0. I'm going to have this squared, so maybe I do like that, plus the same thing on the y-axis, or the second component to be precise, because this distance generalizes to 3D space. You just add another one there, and 4D space, and infinitely high space. So this is one way of doing it, but if you want to practice vectors some more, I'm going to write here, okay, and return it. I'm going to write here, or return subtract vectors v1 from v2, okay, and get magnitude of the result. So get magnitude of the subtracted vectors is going to bring us back here. We have 2 points. Subtract vectors gives us this vector in the origin here, and the magnitude is just its length. So I use 2 vector operations to get the distance between them. It's not going to produce different results, it's just staying in the vector plane, which I recommend. I'm going to leave both codes here, and JavaScript is so nice that it doesn't complain that I have something after a return statement. But some languages complain. So, okay. So now I should have here, inside the segment, a length value. I'm going to debug to see if I have any codes. And to debug here this, because it's hard to visualize, I'm going to write segments. It's a global variable in my console, and check individual, okay. Check individual segment values if they are correct or not. And this says not a number here, so there is a problem. But the particles seem to be just fine. So particle A, particle B is okay, but my length value is wrong. It's problematic. What can be the problem? The problem is here we need to specify the location of the particle. So particle A dot location is the vector. The particle object contains the location and the old location, 2 vectors. So if I don't do that, JavaScript is so nice that doesn't tell me that it's a problem. It just, in this case, doesn't throw any exception or anything. Yeah, I'm not going to dig deeper into this, but I suspect this is the reason why it's broken. So I'm going to do this printing of the segments again, and now I get a length value for the first segment, a different one for the second, and a different one for the third, and so on. But as you can see, during my animation, especially this length here, changes very, very much. So that's what I want to force now, to bring it back to its original size that we stored in these objects. So how we do that? We have the length, so this is the stored value, but let's say now, due to individual forces, or me moving something by the mouse in the future, or wind blowing, or whatever, the points moved some distance. So this is our current distance between the points. What we want to, what may happen is that they get farther apart, or they may get closer together, compressed. But rigid bodies means rigid, no changes. So these differences will need to be added to whatever locations we are currently in their respective directions. Maybe a little bit confusing, but I'm going to calculate the differences. How much longer or how much shorter our current situation is. I'm going to divide it by half and move each extremity halfway in their respective direction. And that is going to keep it fixed throughout my simulation. Well, let's try to do that. It's not hard. Okay, so we moved our particles according to their respective velocities, but now let's write here a piece of code saying applying constraints. And I'm going to apply the constraints for each segment that we have defined, so I'm going to loop the segments. Okay. And now I'm going to calculate the new length. So new length is going to be distance of segments of I dot particle A dot location and particle B dot location. I will have, oh, what did I do? Some strange formatting there. Sorry about that. So I can calculate the distance, and I also have my expected or desired distance. It's stored here in the segments. So it's the segment I of length. This was when it was initially created. So now the difference in length between these two is going to be the new length minus the desired distance. Okay. Yeah. So that's going to be our difference. And now what we want to do is move these new points backwards. Okay? So move these 2 points backwards somehow. Now, to get the vector between these 2 locations, that whatever they are now, we use again which method, which vector operation? To get the vector between 2 points. Sorry?
The distance or distance?
The vector. So to get the vector between particle A and particle... Subtraction. Yes. So we use subtraction. You should already see this pattern. So every time we want this vector between the 2 points, we use subtraction. Yeah. So, let's call it vector. Is going to be subtract vectors of particle A location and particle B location. And now this vector is maybe very long, like 120, 140. But I want to move those values a little bit. How much they moved, this difference in movement, right? So to be able to scale it by the difference in movement, I need first to normalize it. I normalize the vector that I have so that it keeps the direction, but it's a unit vector. And then I multiply it by half the difference. So let's see. Normalized vector. I'm really naming here many variables, even though all this stuff could be written in one line, one horrible line. But this is very good for, especially for educational purposes. So normalize vector, vector. And now, okay, scaled vector is going to be scale vector. Our normalized, okay, this somehow hard to do. And diff divided by 2. Okay, so this is what happened. Oh, okay. Just a second. So now this is our scaled vector that we need to use to move particle A and particle B. So how do we move particle A with the vector?
We scale it by negative.
Sorry?
Scale it by the negative scaled vector.
No, so I want scaling by something, no, I want to move particle A location with my scaled vector. So this is a vector.
Addition.
Sorry?
Addition.
Anyone else? Yeah? Yeah, so it's addition. When we want to move something by a vector, addition. We added the gravity before, we added its velocity vector. Addition. So the particle A location is going to be add vectors, whatever the location is, and our new scaled vector. If this works, I'm really happy because we did many things here. But we also have to move the particle B in the opposite direction, and this is probably what you were thinking before. So we also need to move particle B, but if I write the code like this, particle B is going to go, so let's say this is particle A, and I moved it down. This particle B will move even more down. So I want it to move in the opposite direction, the same distance. And to get it to the opposite direction, we do scale it. So var opposite vector scale vector our scaled vector in -1. So our scalar is going to say we want the opposite direction. Okay? Now, so I did guess that some students will will maybe drop, but maybe not. Who knows? Maybe they're busy. But yeah, this is not too complicated actually if you will try to understand. I save it and I really hope, like really fingers crossed, because many things happening here. Refresh the page. Yeah, just as intended. Like exactly perfect, no problems at all. Okay, I'm going just to try really quickly to do some things and...
I have a question.
Yes.
When we are going all this, we have velocity, and if we just give them all of those particles the same velocity, and we have only one force, so they won't move by the same
If all of them have the same velocity, yes. But if you hit the object on some corner or something, it will start spinning or start doing something else. We don't want everything to just translate all the time. I think what the problem now is most likely something silly like this should be B or this should be A. We will have a break very soon, so I'm just going to try this quickly and hope it works. It works. It actually works. It deforms, but okay, before the break. So you can see the object deforms, but the size of each vector remains constant. This is because of this. So let's say this is the object here. My fingers are not changing their length. Okay? My fingers don't change length, they don't grow or get shortened, but the forces on each individual points here are changing it. If I want the object to be rigid, I need a diagonal. I need something in the middle to keep them also from not doing this. Like if you imagine a pencil or something between my fingers, my fingertips, then I couldn't do this, right? So let's add that and then have a break and then talk and ask questions if you have in the break and so on. But we will get to some really nice things really soon. So I'm going to add a fifth segment between 0 and 2, the 0th particle and the 2th particle. Refresh the page, and now the object doesn't deform anymore, but it spins a little bit. it's hard to see, I'm going to increase these initial velocities even more. So let's put this 6 and 6 here. So now the top 2 points are moving much faster to the right. Okay? If I would remove my segments from here, if I comment them out, and I refresh the page, the top points are, okay, they are moving more strongly, but let's do it even more. Let's do it 9.8 and 9.6. So, yeah, now it's much more significant. So I would expect the object to start rotating more, because the top points have initially had more velocity. So adding back the segments, refresh the page, and because of those 2 points that had a higher initial velocity, our object rotates more but still keeps the constraints. Okay? Okay, I think we can have a 10-minute break, and the ones that have issues here, maybe stay with me and ask me questions. It's not very difficult. If you understand vectors, then understanding why the object doesn't deform now, it's still affected by gravity, should be clear. So let's meet 21%. And just to recap very briefly what we did, we defined 4 particles. Yeah, they are moving particles. The top ones are moving a little faster than the bottom ones, but all of them are moving a little to the right, and they are accelerated by gravity. So they are going faster and faster. And there is no such thing as a terminal velocity. Terminal velocity exists in the real world because of air friction, but we didn't invent any air friction. So these particles are going down and down and down and always being accelerated by gravity. Forever, until I refresh the page. Then we added segments in between them. We added 4 segments around the object, and a 5th segment connecting as a diagonal. That one acts just to keep the object from deforming like that. So you see these points are getting collinear at the beginning, but then they are squeezing themselves in the beginning. So this example from here, I have the rigid edges, but without the diagonal, the object will deform, but it will keep the lengths fixed. So I need the diagonal there, and as a result, the object rotates a little bit because I just defined the velocities for the 2 points at the top to be going in the right direction, and quite strongly. If I put here also quite strongly in the left direction the other 2 particles, the low ones, then most likely what will happen is the object will spin much faster. So now I'm doing this to the object, right? The top moving to the right and the bottom moving to the left. I refresh, and the object more or less is just falling because those forces cancel each other out. They don't move it anymore in some direction, but the object rotates more. Okay, but
what happened? Can you show it again? I didn't understand. What was happening? Why was it rotating faster?
Yes, so I'm going to cancel the segments for a second and refresh the page. So what happens now, these points go to the left, these points go to the right very much. So what happens is more or less this. Before we had points to the right and points slower to the right, so we got something like a little rotation, but mostly moving to the right. But now these forces don't move the object very much, just gravity moves it down.
I have a question for this.
Yes.
Strange effect. So, does your rotation change when you change the order of drawing the points from in your array of 0, 1, 2, 3? What if your segments are drawn in order of 0, 2, 1, 3? Will it make a different rotation?
We are going close to the impressing state. Yes.
Okay.
All the effects that I am doing, all the particles that I am moving here with the velocity vectors, and all the constraints that I am adding them one by one.
Yes.
That also means that if I will add a constraint between the first, and then some other constraint requires the original points to move a little bit, my initial constraint will be violated. We will investigate that a little later, but now I want to show you something very cool. Okay, so let's look at something very cool and go back to these initial points here. So now we have the object moving just like that. But I don't want it to go out of the screen anymore. I want everyone to pay attention now. So I want it to stop at the bottom. Okay? So I'm going to stop it at the bottom. I'm going to go here and say for each particle, if the first component of this particle is going to be less than 0, okay, the location of that is going to be less than 0. I'm sorry. So the location of the first particle, its first component, its x position, is going to be less than 0, then make it 0.
Without looking.
Why?
I'm sorry?
Why component?
Stop.
Yes, I want all of them. I want the object to stay in the scene even if it will eventually go anyway, any direction. So if it's like that, then the 0 component is going to stay 0. Also, if the x is going to be more than 300 was my size of the canvas, I really should make this at least as a global variable, but I'm making some problems in the code, but I'm sure you will spot them and fix them in your projects, okay? And yes, the y component. And now the 10 euro question. What will happen when I save this and rerun the file? Yes?
It will stop going off the things.
It will stop at the bottom.
Yeah. Or maybe at the top.
Well, it still goes down, but at some point it will glue either to the top or to the bottom, or I mean to the top, to the bottom, to the left or to the right. More precise. It will not stop, I can tell you. How about in Kuopio? Who wants to guess what happens to this object when it reaches the bottom, assuming that I'm not allowing these y values to go more than 300 pixels? So
It's going to be destroyed.
Just a line.
object is destroyed.
It will bounce back.
Sorry?
It will bounce back.
It will bounce back.
Yeah.
I owe him 10 euros.
I think that's
It will crash. It will not crash because I have these strong constraints there. They say that the distances are going to always be the same. Let's see what happens. Okay? It's going, going, going.
No, it's not.
What happened?
bounce.
Kind of bouncy. A little bit bouncy, but not that bouncy. Okay, how about if I make the gravity a bit higher? Let's say 2. Stronger gravity. Does it actually bounce it more, or what happens? But it deforms, you see? It deforms, and yeah, it bounces it back a little bit. This is very strange, isn't it? So there is some deformation happening, but I would say this is quite impressive simulation already. I mean, I have some jiggly dog toy or whatever throwing it around.
You made it jelly, very, very nice.
Jelly, I made a very good jelly.
That's it.
Yes. So, this is what was your name?
I'm Henry.
Henry.
Yes.
Yes. So Henry speculated that the order of these constraints is going to matter, and this is very true. You see how jelly-like it is. This is because when I will tell this point to stay still, the other points will move down. Okay? But then the constraints they are trying to apply, but they are going to apply in order. I don't have good slides for this, but I will try to explain somehow. Okay, let's look here in this example. So, if here we want to fix these constraints, if this point went up and this point went down and this point went that way, okay? So I will first fix the constraints for this segment right here. And that means that the length here has to be the same as this line. And I'm going to fix it with half the distance in each direction. So there, this one is fixed, okay? And now I'm going to fix this horizontal change. I move to be the same length as this line. So this one will go here a little bit, and this one will go here a little. But now this segment is too long. So this is why the jelly effect is happening.
Can I suggest that you can easily make another diagram to make it more rigid? Can you try that?
Yes,
That
I
would
can
be
try.
Very nice.
I can try, let's see what happens. So suggestion was I can make another diagonal from 1 to 3 and see what happens. So it would supposedly make it more rigid. Something happened, it's different than before, but it's not more rigid. The problem is just that any time a modification happens, like what I showed here, and then another segment is fixed, the first segment broke again. I mean, it didn't break, but it violated the constraint a little bit. To solve this problem, this Jacobsen paper, read this paper, it deserves attention. They iterate these constraints many times. So what happens is the first segment fixes, the second fixes. Then the first fixes again, then the second fixes again. And it repeats, let's say, 100 times. I'm going to just repeat this block of code where I'm fixing the constraints 100 times in this while loop. And now let's see again our effect. But again, the previous was a nice effect.
Still.
Yes, what happened?
Did you remember to decrease some?
Oh, yes, if I would not have remembered to
Yeah.
decrease, I would have an infinite loop.
Infinite loop. Yeah. 1,000?
We can try, but I suspect something is wrong. Yeah, very strange. And one here, what happens? So no iterations basically. Okay, it did do something. It did do something. Let's try to also remove that extra segment that we try to add for stability, just out of curiosity what happens again. So this was the original, I think, with no iterations. Yeah, and 1,000 iterations. It is not as much deforming. Let's try 10,000 iterations, if it will do some. Luckily, this computer can do iterations. Okay, at some point, some deformation will happen, apparently. And the main reason for, yes?
Did it say in the original paper that after every iteration it will make a smaller and smaller change so that it will freeze the points?
Yes, yes.
That could help a little, but I don't know.
Maybe, let's try. So you want our difference vector not to be divided by 2, but to be divided maybe by 20. Then our difference, it will make many small changes, and maybe it's going to stabilize. Okay, I have to say that this is new to me, this original configuration here. Okay, this original configuration, these angles, whatever, make it deform much more than what I expected, but deformation must happen to some extent. And I will try to explain why. The reason is these points at the bottom are experiencing an instant stop. Something that in physics wouldn't really happen very often unless this kind of very hard collision. So what happens now, this point stops instantly, but all the other points move down a little bit. And then in this constraints part, these points that are moving down and should move down are fixed by being moved upwards, so that the original point at the bottom has the constraints still existing. And because these additional points, instead of moving down, may move a little bit upward, they start pulling the object against gravity. And that is what causes the bounce effect. Yes?
Do you like this fix? I don't know if it's a quick fix. Every time, just like in your loop, there is an if clause that says that if the boundary is hit, set a flag. And then in your loop, if the flag is set, no other points are updated by the force, so that it will be rigid. You know, it will stop applying the effect of force to other points when any of the points are hit.
Yes. Yes, but the problem is that then your point gets stuck to the wall.
That's true.
That's true. We can experiment with that. In fact, let's do something very similar. I will, but not exactly the same. I will add to our particle a new attribute in the constructor. I will say is static. By default, it's going to be false, but one attribute here, I said I want it static. So this particle will not move no matter what. To do this, I have to, when I update the location of each particles, I have to check if it is not static. So this is going to be quite interesting simulation, I think, because I can check if it's not static, I'm going to move it. But also here, I have to check if particle A or particle B are not static, okay? Because this is moving them also. So if particle B is not static. I'm going to move it by the vector, and I'm going to do the same with particle A. So what happens now is that one point is not going to move
You miss in the conjecture.
I am missing what?
In the conjecture sense function, when you need to know the particle, conjecture.
I'm sorry, can you repeat?
Construction.
Yeah,
Constructor.
conjecture function.
Constructor. Constructor.
Constructor function. Oh, I'm sorry. Thank you. Yes, thank you very much. So in the constructor function, is static was not stored anywhere. I really like it when people are paying attention. Okay, so now this thing doesn't fall anymore because this point here is static, right? It more or less is going to oscillate. It's like a pendulum. Okay? Now I'm going to implement something quite nice. I'm going to implement a piece of code that when I click on a link, it will destroy it. And then we will see how this turns into a chaotic pendulum. In physics, when you have pendulum connecting many bars together, this is called a chaotic pendulum or a multiple pendulum, and it tends to be very different every time you try to run it. So I'm going to write a function that when I click, I will get the nearest segment and remove it from our segments array. So let's see what happens. It will take a little time, but more or less on mouse down, I already have here a function for get cursor position. I will need a function for get nearest segment. I will have to write it, get the nearest segment to the location, and then I will have, let's say, segment index here. And then I will take our segments array and use the splice method. Splice method removes or adds elements to the array. But if I write here segment index and 1, it will remove from the segments the one at the specified index. I just need now the function for getting the nearest segment, right? And it's quite easy. So function get nearest segment to a location. And what I'm going to do is I'm going to iterate through all the segments. And first I'm going to calculate their midpoint. I will have to click close to the middle of the segment to remove it. It's easier this way, even though maybe not best user experience. Midpoint is going to be equal to average segments of I, particle A location, and the particle B location. So these two particles define the segment. If I'm going to calculate the average, I'm going to get the midpoint. Okay. And then I'm going to calculate the distance to this midpoint. So I have already the distance function from the location parameter over here to our newly calculated midpoint. Oh, sorry, I did something stupid. And then, if this distance is smaller than our minimum distance found so far, our minimum distance is going to be replaced by the current distance, and our index is going to be I. So we initialize minimum distance with infinity, something very large. And our initial index, which we return, let's call it 0. So we will return the first index, but it will update to the one with the minimum distance to our click location on the canvas. And I will return index. And just before I finish, I have to say I don't have the average function, okay? But very easy to write it, so I will go to where I have my vectors here, and I will write average function of v1 and v2, and this is just going to be v1 of 0 plus v2 of 0 divided by 2. Now this you can also solve with vector functions, okay? It's actually the sum of them and then you scale them by 0.5. You should practice this at home. And now if the code works, it works. If not, we will have bugs. Okay? I will try to cancel this link. It works. I'm good today. I'm really good. So I canceled that link. I cancel also this link. So now you see this movement happening in real time with my interaction, right? Let's try again. I'm gonna cut the middle link, and now the object does this kind of funny behavior here. I could cut the top two links, and now the object actually falls down. But notice here, there shouldn't be a bounce. There is no bounce at all because I don't have enough constraints to force my upward movement of the still falling dots. So this is how I found out why those things were bouncing. I just played very much with this interface. Okay. And now
I'm going to add a box function to your, because now anywhere in your canvas it will remove the closest. So to avoid that, do you want to check that you are inside the
bounding box? Okay.
Closest to the segment.
Yes. So Henry means that if I click here now, okay, it will remove this top link because I don't have any condition of being anywhere close to this link, right? So let's try it. Yes. So I clicked here and that part fell down. The problem with your solution is if the vectors are vertical, then the box will be aligned. And if I'm gonna have to click exactly on a line, I'm very likely going to miss the exact pixel.
Let's make it 2 circles.
Maybe something like that. I
Okay.
will let you
Very good.
experiment with these things. That will be your task. I'm not going to do it now because I still want to show something better. But distance to the segment is not calculated correctly by me. I'm calculating distance to the midpoint. I would like to calculate distance from here to here. This could be solved in very many ways. Geometry-wise, you can calculate the triangle from my point to the other segment, calculate its area using Heron's formula. So this is the formula you can use to calculate using the perimeter of the object. And it should be also equal to the height multiplied by this base divided by 2. So if you have the base, if you have the area using Heron's formula, then you can infer the height. This is one way of doing it. But there are more ways, even vectors can be used. Some dot products and some interesting things, but we will get to it later. Before that, we still have time. Let's do the hitman. I want to shoot somebody. And I'm gonna cheat like really badly and copy code. But it's nothing for you to be scared of. I mean, if you went like, if you followed this far, then this is trivial. I just made more particles and more segments here, more or less the same way that I did the house in the previous lecture. So I just defined some points and some segments between these points, okay, in a text file. And see here, interesting, the object is actually falling down. It's falling down because of the order the segments are processed. You would expect this object to fall perfectly straight down, but the constraints are added one after the other. So it somehow affects a little bit how it falls. Those iterations that we had here, I'm pretty sure that if we move and have more of them, it should prevent the object from falling, I really hope. Okay, not very much.
No, it's not.
Okay, something could be buggy. I'm going to also reduce the gravity a little bit. So if I reduce the gravity, it's not going to pull as hard on them. Okay, I really have to say something here. This gravity is extreme. I am displaying these animations at an absurdly slow interval here because I wanted to display in Kuopio well. So these objects are actually moving in really, really slow motion, but they are moving very much. This is the problem. This is the reason why everything is deformed so much. I will speed up this a little bit and add a normal value for the gravity with the risk of maybe sacrificing how the result will look like here. But more or less, this gravity is reasonable. What you see now. So before I was adding like really, really much, it would instantly flatten if this would be 10 here. So, okay, that can also happen. But it, yeah, the time difference also impacted a little bit. But okay, simulation time. So now I'm gonna hit his hand. Well, no surprise, his hand fell down. But if I'm gonna hit his leg, okay, I hit something else, but and it looks very strange. But I have to say that in the beginning, these animations looked quite strange. And also the fact that my skeleton here, I made it quite quickly. It's not exactly the same one that was used in Jakobsen's paper. But you see that the person is falling more or less in a way you would expect, even though now he's hardly recognizable. So, yeah, can be used for that. Okay, I think that we've seen many things today, and some things are understood, some things are not 100% understood. I understand 95% of these things. So even though this simulation... Okay, very, very interesting thing. This object that is swinging here, okay, on the top, it will stop. And this should shock everybody. I'm going to try to stop it. I will add here a huge speed for the animation. Okay, and let's add also a little stronger gravity. And let's see if, because now it's hardly noticeable that it's slowing down. But with this thing added, we can see that it's slowing down. And eventually it's actually stopping. And this should be extremely surprising to you because I have not implemented any friction in this code. And there is no friction. I mean, if, for example, I these points, see, they are moving at the bottom without friction. They are slowing down because of the constraints when hitting each side of the wall, but they are constantly moving everywhere. So the reason for this slowing down and stopping is because it's very, very technical, but the reason is mostly I'm approximating all the time. This is not a continuous movement, it is a discrete movement. And when I'm moving the point and then applying the constraint, it's just not the same as the continuous movement would be. The point is a little bit different. You can think about it, but I wouldn't bother. So that explains this. This is not a perfect simulation. This is a simulation very useful if you're going to make games, or if I'm going to make the spider web at some point, because more or less it's going to be something like that, but a little bit more intricate. But it makes really, really useful effects to happen. And before you go, here and here, we actually have a couple of more links. So this link is Jakobsen's paper made into code, more or less what we did today, but the code is in C, I think. I have to see, just a second. How do I see this?
Control click.
Control click.
Control click.
Control click. Yeah, but it opens in Edge. And,
Yeah.
okay, so this blog post, it's more or less what we did today, but it's in C and it has operator overloading, and it has this. It describes collisions, and it describes collisions, how to implement them, and it's not very, very complicated. One of the tasks for next week's exercise is to do collisions, and more or less it will mean to find this vector and also move the points halfway in that way and halfway in that way with respect to that vector. All the method is described here, but collisions is not the only way to pass next week's exercise if you find this too difficult. But it's the most interesting to me. So you would have objects hitting each other and colliding. If you really want to impress me, take the planet experiment from last time, make asteroids instead that look somehow different shapes, and then when they hit each other, they collide in different ways and start spinning and whatever. So that would be the passing exam without the exam. But check this one, and by the way, small promotion, even though I am not extremely proud of it, I implemented this actually 10 years ago in ActionScript for Flash in Romanian language. There is an article there. Yeah, so this is me in my second year of university. Abstract is in English, but everything is in Romanian, and it actually even describes collision, but I don't have access to this document anymore. It's very strange, but yeah. So anyway, tomorrow we do something completely different. We have a break from all these vector stuffs, and we talk about image processing and object recognition. Okay, thanks everyone.